Hello, I'm Michael O'Connell, and in this video I'm going to demonstrate how to solve an ideal gas problem in which there are two unknown variables. In this problem, we have a container of water that's left open so it's exposed to the air. And what ends up happening is that we close the container and we seal it so that the air is still inside, and we heat up the sample to a certain pressure. So let me go over what's been given to us in the problem about the initial state and the final state. So initially we have a pressure of 101,325 pascals, which is 1 atmosphere. We have the number of moles of water in the vapor phase. We have the initial temperature, the total mass of the water that we start with, and the final pressure. What we're trying to find is the final temperature of our sample as well as the total volume. In order to solve this problem, we need to describe the relationship that these variables have to one another. And to do that, we're going to write equations based on what we know. And we are going to begin this by starting with one of our unknowns. Let's start with the volume. So we can express the total volume as the sum of the volume in the liquid phase and the volume in the vapor phase. Because this is what's going to be left over. We're going to have material in the gaseous state as well as material in the liquid state as well. We can do something similar with something we know, like the mass of the water that we started with. So because mass is going to be conserved in this situation, since we have our container sealed, so nothing's going to be escaping, we can express the total mass of the water as the sum of the mass of liquid water plus, the sum of the mass of liquid water and the mass of water in the vapor phase there. Let's do the same thing here with our final pressure, because this is important to realize when we're dealing with ideal gases. So in this ideal gas, we are assuming that the particles of air and the particles of water essentially don't see each other and stay separate. And what that means for our final pressure is that we can actually express it as a sum of partial pressures. In this case, the two components we have are air and the water vapor. So let's express that here. So we have the final pressure is going to be equal to the final partial pressure of air plus the final partial pressure of water. Okay, so we're going to need to express both of these things, right? So let's start with water. What's important to realize here is that we're starting with a liquid sample of water. So what's going to happen is that there is going to be some equilibrium established between the liquid water and the water vapor. And what that means for us is that we are along the vaporization curve for water, which is actually modeled by the Antoine equation. So that's what we would use here to determine the final pressure of the water vapor. And that's going to be dictated by the temperature of our liquid. So the Antoine equation is the log of, and it's actually the common logarithm, so log base 10 of the vapor pressure. This is going to be the final vapor pressure of water, equal to coefficients A minus B over coefficient C, plus, in this case, we're in the final state, so this is going to be the final temperature that we're adding. And I'm going to rewrite this actually so that we have 10 raised to the power of this here, so that we express this set equal to our final vapor pressure of water. So let's rewrite that here. So this is just going to be 10 raised to the power of A minus B over C plus our final temperature there. Okay, excellent. So there's a couple other things that we're going to need to do here. We should probably express the volume of liquid, and what that's going to be is it's just going to be the water. Now, the only caveat here that we have to take into account is that this volume of liquid is in the final state. So it's the water left over, which is represented by the mass of water in our liquid phase divided by the density. So I don't know why I looked down here. I thought there was like a bug or something that kind of scared me. So sorry about that. So this will be divided by the density. I'll just put rho W. Okay. So that's the volume in our liquid phase. We can use that to write an expression for the volume in our vapor phase. So I'm going to write that kind of over here if that's okay. This would be the difference between the total volume and the volume of the liquid, which would also be the total volume minus the mass of water in the liquid phase divided by the density. Okay, excellent. So let's see what else we have here. Okay, so we have the partial pressure of air, and we can express that with this expression here, but what we need to account for too is actually the initial state for this situation. So I'm actually going to write a different equation here that will take that into account. And let's use, since we know the moles of water in the vapor phase, we would also like to know the number of moles of air that we have as well. So the number of moles of air is going to be equal to the initial pressure times the volume in our vapor phase divided by R times the initial temperature. Okay, so we have an expression for that. I want to keep hacking at this equation up here with the moles of air that we have initially. One thing I have here is I have the initial pressure, and that's obviously not going to be correct because we also have water vapor that we have to account for. So I'm going to re-express that part of the equation. And we also need to take into account this volume of vapor that we would have initially. So that expression may look a little bit different than this expression over here for the volume of vapor. So let's try to rewrite this more accurately. So we have the number of moles of air is equal to the initial pressure. So we know the initial pressure is atmospheric pressure given to us there. But what we're also going to want to do here is we're going to subtract the partial pressure of the water vapor initially, which could also be found by using the Antoine equation. So I'm going to just write it here as PIW for the partial pressure of water vapor initially. So that difference between pressures is going to be the initial partial pressure of the air. Then we're going to have the volume. Once again, this is initially. So this will be the total volume minus any volume that's in the liquid phase. So notice that this is not going to be the mass of the water in the liquid phase divided by the density of water, because this mass of water in the liquid phase is referring to the mass of water that's left over in the liquid phase. So we want actually the mass of water that we started with, because this is initially, we have that 1 kilogram of liquid water up there in our container. So I'm going to express this as the mass of water total divided by the density of water, instead of the mass of liquid water divided by the density of water. So there we have that, and all of this is going to be divided by R times the initial temperature. And once again, I should note that we can attain this initial partial pressure of water vapor with the Antoine equation again. Let me just write an expression for that. So we have the initial partial pressure of water vapor would be 10 raised to the power of these coefficients A minus B over C, this time based on the initial temperature of our liquid water. Perfect. There's one last thing that I want to write an expression for before we try to find the final temperature and the total volume of our container by using Python. So what I would like to describe is the number of moles of water vapor that we have, similar to what we did for the number of moles of air. What we have to remember in this case, though, let me make this a subscript there, is that this is describing the number of moles of water in our vapor phase after we've heated our sample. So this is the final state, unlike the expression we have for the number of moles of air in the initial state. So this would be based on our final partial pressure of water. This time we actually can multiply by the volume of vapor in this case. It will be expressed correctly because we have this expression here, which is the total volume minus the mass of water in our liquid phase divided by the density of water. So that's perfect for us. And all of this is going to be divided by R. And again, this time we're going to be using the final temperature because we're in the final state. Okay. Now, before we head over to code this in Python and find our two unknowns, I would like to explain the importance of this equation and this equation. So the reason that this is going to be able to be solved in Python is because we have two unknowns, the final temperature and the total volume, and two equations. The equations actually are already given to us here because we have the number of moles equal to 0.3 for the water vapor after we heat our sample, as well as the final pressure of that sample as 200,000 pascals. So what we're going to do is define a function and express these relationships within that function. And what we are going to do is actually find the root of an expression that we return. And what that means is setting that expression equal to 0. And what we're actually going to do is use the root function from SciPy, which is a Python library, to change these values because we'll put in guesses for the final temperature and the total volume. And it will adjust those values such that the expression we return is 0. And the values that it comes up with will be our answer. It will have the final temperature and the total volume. And you might be wondering, well, what is that expression? Well, that expression is going to be based on the two equations. Just like the inputs for our function will be probably a vector of these two unknowns. So what our expression will be based on is those two equations. Here we have the final pressure and the number of moles for water vapor after we've heated our sample. And the expression will actually be just the difference between the final pressure and the final pressure that we specify that we want as a parameter before we write our function. And the same thing will be done with the number of moles of water vapor. So basically, you'll have, as one expression, the number of moles of water vapor subtracted from the number of moles of water vapor. I'll just put SPEC because that's what we're going to specify, because we're specifying that we want 0.3 moles at the end. And so this is going to be one of our expressions. And we would do the same thing with pressure. We would have the final pressure subtracted from the final pressure that we specify. And obviously, we want these to be the same. And if they're the same, the difference is going to be 0. And that's what the root function is going to be super effective for in the next part of this video. So now, let's go try to solve this problem and find the final temperature and the total volume of our container by using Python. To solve this problem, we're going to need to relate the partial pressure of the water vapor to the temperature, both in the initial state and the final state. I'm going to use some code that's already been written in a repository. To use that repository, I'm going to need to clone it into our Python code. So I did some research before this about Python shell command and how we're going to use that. And what that will mean for us is that we are going to have to start this off with an exclamation point. So let's make a new notebook here and start that off with an exclamation point. And like I said, we're going to have to clone this repository into our code. So get clone is what we're going to use. And this exclamation point allows us to use the shell command in Python and download this after I hit Shift Enter. But what we need here is the link. So I found this repository on GitHub. I was looking at it before. So the repository is CHE-tools. So that's what we are going to use. And notice it has some modules in here. And those are going to be important because what we're going to have to do next is establish the path when Python goes looking through the files that are uploaded to it. So that will be very important for us here in a second. But first, let's actually clone this. So I'll hit code here, and I can hit that button there, and it copies it. And I can just put the link right in here. And if I hit Shift Enter on this, we're going to have it cloned into our code here, in which it will be downloaded in this file over here. So before I do that, I'm going to want to specify the path. And to do that, we start by using the import sys sys, and that's what is actually going to allow us to specify this path through the system. And do that. Okay, so we have everything cloned. And here are our files. So we have bin, boot, content, all these files that Python is going to look through. So we need to specify the path. We need to specify the directory that it should go to first. So to do that, we see that under content here is my CHE-tools. And that also has the modules that we're going to want to import later. So let's specify this path first. So this will be sys.path.insert. That's what we're inserting here. And we want this to be the first in the order directory that Python goes looking through the files. So we'll put 1 and then in quotes /content because that's the first folder there. I need to spell it right. And then CHE-tools. There we have it. Perfect. The next thing we're going to do here is we're going to import our module. Specifically, we want the tools module because that has code that I want to use to relate the water vapor pressure and the temperature with the Antoine equation. So let's examine what code is inside of there. And I was looking at this beforehand, and this is actually one of the Python code files, che.py, that's within tools. So I'm going to back out of it so that you can see it. So that's in this module tools, che.py. And the reason I was interested in this in particular is because it has a class that will be useful for us. So this class here, props, is going to allow us to instantiate it with a certain compound, in quotes, an object, and can allow us to compute various values like the vapor pressure based on the compound's properties. And it gets those properties from the data file, actually, or the data module, I should say. So this has a lot of different text files here for different compounds, ethane, ethanol, cyclohexane, but we want water. And if I go into the water text file, so we see the molecular weight, critical temperature, melting point, normal boiling point, all of this stuff. And as I was scrolling through, we find vapor pressure. And we actually see there's 5 coefficients here. And that's because the version of the Antoine equation being used here is actually even more sophisticated. So it doesn't have just those 3 unknown coefficients. There's actually A, B, C, and D and E as well. And that's because this is all imported from KimCAD. And I was looking this up beforehand just to verify that those coefficients were correct from equation. It said it was number 101, which is, right here. Yeah, this is what I was looking at. So these are those coefficients. And as you can see, they do correspond correctly. So let's go ahead and import that module and use CHE there. So we're referring to the Python code that we want to use here. I'm going to title this as X just so that it's something I can rename it later. So let's import tools, because that's the module we're referring to, and then dot the file name, so CHE, and we'll refer to this from now on as CHE. Perfect, so we have that. The next thing I want to do here is use that class I was talking about, props. So let's store this all under one variable. So I'm going to call this properties because it's going to be the properties of water here. Properties. And we are going to refer to that code, so CHE dot, and we want that class, which is props, and let's instantiate it with our object. Water is the compound that we're referring to. Take just a second here. Okay, and we're ready to go. So the next thing we want to do here is specify everything that we actually know. So in this problem, I pulled it up here because I knew I was going to forget what we do know. So we know the initial pressure and temperature. So let's start there. So initial pressure is 1,325 pascals. The initial temperature, 298 Kelvin. I like to specify the units on the end just to make sure that we're doing everything correctly. We also were given that we started off with the total mass of water at 1 kilogram. Oops, didn't want to do that quite yet. We know that the number of moles of water vapor that we want, and like I said, this is one of the equations actually that we're given, and this will be very important for us in trying to find the solution to this problem, is 0.3 moles. We also know the final pressure. I'm just going to use 2e to the 5th, so 200,000 pascals. Let's see if there's anything else we know. Not that I'm aware of. I think we also know the molar mass of water, so I'll do capital M, W for that. And that is going to be 18.015. And I'm going to put E to the -3. And the reason I'm doing that is because we need this in kilograms, not grams. So I'll actually specify that this is kilograms per mole, not grams per mole, which will be important for us. And I think we're ready to go. Now we're ready to find the total volume and the final temperature. So to do this, like I said before, we're going to find the root of a certain function that we create. So the roots of a function are the points on which the value of the function is equal to 0. So to do this, what we're going to return from our function is the difference between the final pressure that we specified in our parameters and the actual final pressure that's used in our equations within our function. And we're going to do the exact same thing with the number of moles of water vapor. So once again, there are two unknown values that we're trying to find and two equations. So what the function is going to do, or what the root function that we are going to use will do for us, is adjust the total volume values and the final temperature values based on guesses that we specify. And it will find the total volume and the final temperature that makes our function return equal to 0, which again is the difference between the actual water vapor pressure value and the theoretical or ideal water vapor pressure value that we specified as 200,000 pascals. So when we get back to our code here, I'm going to show you here that I changed our parameter for the number of moles of water vapor and the final pressure with underscore ideal. And again, that's to specify that what I'm entering here is what we would like our sample to be after we have heated it. But when we relate the number of moles of water vapor and final pressure with other variables in equations within our function, I'm just going to use NWV and PF respectively, because these are going to be the actual values, not just the ideal ones that we would like. The goal with the root function is to find the value for the volume and the value for the final temperature that make the difference between the actual number of moles of water vapor and the ideal number of moles of water vapor in the end that we specify equal to 0. And we're going to do the same thing with the final pressure. So with all of that out of the way, let's start writing our function. So we're going to define a function x, and it will take in a vector of our two unknowns. We'll call that y. And we will unpack this. So final temperature and total volume is what we're going to want here. And now I'm going to start writing the equations. So now we're ready to find the volume and the final temperature. Let me finish writing my function here, now that I've put in my equations. So what we want to return is the difference between the actual number of moles of water vapor and the ideal number of moles of water vapor. So let's write that here. And we're going to do the same thing for the pressure. Some square brackets there. They're separated by commas. So those are our two equations. And then we have two unknowns that we're trying to find. I use the root function from SciPy, which is another Python library. It's also used with matrices, linear algebra, statistics. So it has a lot of different functions that you can use. So this is from Optimize, so scipy.optimize.root. And what this will do is it will take in our function, and then we'll put in two guesses, in this case, because we have two unknowns that we're trying to find. And it will use that to adjust those values for the volume and for the final temperature to make our function here, so this is with two equations, our return, to make these equal to 0, right? That's what we want to happen. So let's see what happens when we try this. So root, let's put in our function, which is x, and then our vector of the two unknowns. So let's guess the final temperature. It's going to be higher, obviously, than 298. Let's just add 100 kelvins to that. So we'll put 398. And for the volume, it's going to be returned in cubic meters, which is not going to be very big. So I'm going to just go with something small. Let's try like 0.08. Okay, see what we get. Okay, so it says local variable, the VL, which is the volume in our liquid phase, is referenced before assignment. So what this means is that we need to write our expressions in proper order so that they have an assignment before they're referenced, as this says. So let's try to do that. Now for one here, you notice that I have commented out the partial pressure of the water vapor in the final state. And the reason for that actually is because we're able to compute that using the Antoine equation. But instead of typing the Antoine equation into our code and being forced to use the coefficients A, B, and C, or D and E as well if we're using the more complex Antoine equation, we can use one of the functions that was in the props class that we have up here. So we've instantiated it with the object water, which is our compound. So we can use some of the functions that were within this class to find out different things for water. In this case, we want the vapor pressure, and we can use one of those functions because if we remember, there was a function in there for vapor pressure that I looked at, and let's write code for that. So this will be properties because that's the variable I specified this under. Properties. Okay. Properties dot, and a lot of these come up. I was looking at these before, so there's a couple that we're going to use. We're definitely going to use pVap because that's the one for the vapor pressure. We can also use rho L, which that is actually super awesome because what that's going to allow us to do is account for the fact that density changes with temperature as well. So we're going to be able to do that within our function as well. So let's do pVap, and we'll put in the temperature. In this case, we're in the final state, so it's denoted as TF for the final temperature. Okay? And since this is a value that we know, I'm going to put this up here at the top. Okay. So let's see what else is going to incorporate something like this. And if you look down here, I actually have the number of moles of air with our ideal gas equation. So I'm going to move this up here. And we can actually do the same thing we did because we have the vapor pressure of water initially. So I'm just going to copy and paste this in here and change this to the initial temperature. Okay? We have our total volume, which is an unknown. And then we have the total mass of water to start with. And the reason we're using the total mass of water is this is initially. Okay? So initially, we're assuming all of the water is in the liquid phase, and then we have the density here. So the density is another thing that I was going to use this for, so let's do that again. So properties dot rho L, liquid, and then we'll put in the temperature. Once again, we're using the initial temperature. Awesome. So now we have that expressed. Let's see what we need next. So we have the mass of water total, but we're also going to end up needing something with the mass of the water in the liquid phase in the end. So let's write an expression for that. So that's going to be the mass of the water in the liquid phase is equal to the mass of the water total subtracted from the mass of the water in the vapor phase. Now this we can calculate, and this we will want to use our ideal value because this is something that we want to calculate. So let's calculate that based on the number of moles of water vapor, and again, this is the amount of moles that we specify that's going to be there. And we're going to multiply that by the molecular weight. Okay? So now we have a value for that. The next thing we should examine here is we're not going to really need an expression explicitly for the total volume since that's an unknown. But we do need expressions for the volume of material in the liquid phase as well as the volume of material in the vapor phase. So the volume of material in the liquid phase is going to be the mass of water in the liquid phase divided by our density again. So properties dot rho L, and in this case this is going to be based on the final temperature. Okay, because this mass of water in the liquid phase is the mass of water that's left over after we heat up our sample. Okay, so that's awesome, so we can get rid of this. We're also going to need to express our volume of material in the vapor phase. So the volume of material in our vapor phase is going to be equal to the total volume that we don't know minus the volume of liquid, VL. And we do have that defined here. So see how we're just doing this all sequentially so that everything checks out. Now, there are going to be two very, very important equations here that I have from the whiteboard, and that's the final pressure here and the number of moles of water vapor. And those, we don't want to use our ideal values because these are what is expressed here, right? In fact, there's a little typo there. So we do want expressions for the actual final pressure and the actual number of moles of water. And we just want to make sure that what we're using with those expressions are things that we already know. So let me move this here. I'm going to put those two equations last. Okay? After we've defined everything else. So we have our volume of material in the vapor phase. The last thing that we're really going to need here is what we have expressed here. We have the final pressure of the air, and we essentially already have this expressed as well, because we have the number of moles times the constant R times the final temperature, the volume of material in the vapor phase. All of that is already defined, so we are good to go. And we do have one issue here. We have the total mass of the water is referenced before an assignment. Okay, so let's see if we can fix that. So let me try to see what the problem is here. And we have this used again. Now, one thing I just noticed here, we actually already have the total mass of the water, so we don't actually need this. That's probably why it was causing us issues there. So that is my mistake. It says R is not defined. And that's because R isn't defined. So we want to make sure that we have all our constants written up here. And R is going to be equal to 8.314. I'll comment out the units here just for completeness. So this is going to be joules per mole Kelvin. So let's try this one more time. Okay, we have results here. So as you can see here with our array, we have 3.66 times 10 to the second and 1.26 times 10 to the negative second power. So, like I said, this is the volume in meters cubed, and this is the temperature in kelvins. So now that we've found the volume and the final temperature, I think that wraps up today's video. So I hope that helped you understand how we can actually solve a problem with an ideal gas in which there are two unknown values.